Okay, lastly, we're going to talk about Dijkstra's algorithm. That's how you pronounce his name. It's I don't know.
Foreign.
Definitely foreign, thank you. Somewhere in Europe. But before we do that, let me go ahead and recap depth first traversal. If you start at 0, it goes 0, 1, 4, because it started at 0 and then tried to go as far as it can. 0, 1, 4, can't go anywhere, back to 1, can't go anywhere at 0. You can go to 3, you can go to 2, you can go to 5. Did they decide to go to 7 yet? 7, can't go anywhere. Go to 8, can't go anywhere. What number are we missing? 6, which can go to 7, but can't go anywhere. You can go to 4, but can't go anywhere, and then they just put off 9. All right, breadth first ordering. 0, adding 1 and 3 to the queue. Visit 1, add 4 to the queue. Then your next visit is 3 because he's at the front of the queue. When you're at 3, you add 2 to the queue. When you pop the queue, 4 was at the top. Can't add anything, so you go back to 2, add it, which adds 5 to the queue. Then when you're at 5, you add 7 and 8 to the queue. 7's at the front. You visit that, can't add anything, pop it, 8, can't add anything, and then of course 6, which would add, you would look to add 4 and 5, but you don't because you've already visited that, so the queue is empty, and then you add 9. Shortest path. Why do we want to know the shortest path between two things? Performance. Right. When do y'all use this? Designing airport layouts, kind of, yeah. Oh yeah, yeah. Google Maps.
Yeah.
Google Maps.
Google Maps.
MapQuest, right. So this is the general algorithm Google uses, although there is definitely a bunch of optimizations they have done to this algorithm, but just FYI, this is what they do essentially. They do a lot more optimizations, but the general algorithm is the same. So the idea is you want to get from one point to another. Wow, we have a lot of confusing things. All right, it makes a lot more sense, I think, to think of it pictorially. So here we have 5 locations, and you can either think of these weights. By the way, the weights can be anything. It could be miles or it could be time, depending on what you want. Which one would you prefer, miles or time? Time.
Yeah.
Time
It's a
in-
small number, time, that's a large number.
In minutes?
Time.
In seconds? It's, we'll do minutes. All right. So the question is, what we want to know, what's the time between 0 to, what's the fastest time from 0 to 1? Okay. What's that? It's not 16.
13.
I think it's
13.
I think it's 5. Well, we'll find out. So, you have an array of 2 things. First array is your smallest weight, which keeps track of what the smallest weight is from your current location to everywhere else. Think of infinity as -1. So when you're at 0, you can go directly to 1, but that costs 16. You can't go to 2, so you put infinity. To go to 3 costs 2, and to go to 4 costs 3. Y'all see what I did there? Oh wait, I just saw 3 to 1 is 12. Anyways, ignore that. What I said earlier. All right, do you see how smallest weight got initialized? Everyone good? Okay. All right. Weight found is just to keep track of what nodes you have visited. I think it makes more sense to just call it visited. But since you visited to 0, you just mark that as true, and then you update smallest weight. What you do next is you go to the next node you haven't visited, and then you update your smallest weight based on that. Actually, you go to the next node that is the smallest that you haven't visited. I'm sorry, I said that wrong. You go to the next node that has the smallest weight that you haven't visited. Which node would that be? 3. Okay? So you would visit 3 next because it's the smallest. So when you visit 3, what you're going to do is you're going to update these weights to see if there's a shorter path. So you're at 3, you can't go back to 0, so you leave that number alone. You can go to 1, which is 12. But to get to 3 costs 2, which means your total weight would be 2 plus the weight, this weight, which would be 12. And therefore, that weight would change, this weight, I'm sorry, over here to 1 would change to a 14, because you're signifying going to 3 has a cost of 2, and you're adding the extra cost of going to 1, which is 12, which is less than 16, so you would update it. Y'all see what's going on here?
Yep.
Can you go to 2 from 3?
No.
No. You're already at 3, so it doesn't matter. And going to 4 would add another 7, which is not worth it because 3 is already lower. There we are. Okay, yeah. Ignore the iterations, it's more. Yeah. Okay, so now 1 is down to 14, that's great. We've already visited 0 and 3. So now we're going to go to the next smallest, the next node that we haven't visited that's the smallest, which is what? That'd be 4. Because the 4 is less than 14 and also less than infinity. Okay. So when we go to 4, what are we updating? Well, you look at all the nodes you can visit. From 4, you can visit 1. How much does it cost to go from 4 to 1? 10. How much does it cost to go from 0 to 4 at this point? 3. So then what would be the new cost to get to 1? 13, right. All right, so we're going to update 1 to 13. How about 2? 4. 4 plus,
-1.
well, hold on. It takes 3 to go to 4. So you're going to add 4 plus 3, so 2 is going to be updated to 7. And then can you go to 3 from 4?
Yes.
Yes.
5.
What would be the cost? 5 plus 3, which is 8. Would you update that? No, because that's greater. Let's see, do we do that? Yep, 13. 2 got updated as well. Great. All right. What node are we going to visit next? Yeah, we'll visit 2 because it's the smallest, has the smallest weight of the nodes we haven't already done. All right, so we're at 2. Where's 2? Right over there. Where can you go from 2? Well, you can only go back to 1. So what are we going to do?
Add 3.
Which is 10. So we can update anything? So, right. Right. So do y'all all see that? At this point, we're going to update the cost to go to 1 with the value 10. And then you visit node 1, but you're not going to do anything because there's what? Well, you can go to 2, but 10 plus 5 is not going to be less than 7. So we're done. Y'all see how this algorithm works? All right. So that's Dijkstra's shortest path. Notice it actually gives you the shortest path from where you are to any other node in the graph. That's just how the algorithm works. Okay, we are not going to go beyond that today. We're done with that. All right. So, let's do it for this problem. See if I can get the good picture right here. Oh, that's so beautiful. All right. From 0 to, wow, this is not going to be helpful. We got to add some more numbers. All right, give me some more numbers, guys.
7.
290.
That works. 4 to 0. Or 0, yeah. 17.
425. All right. So what do we have? We have 6 nodes? Okay, great. 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5. Oops, 1, 2, 3, 4, 5, 6. Good. So we'll initialize them all to false. We're going to visit 0. We want to know what, well, we'll just run it from 0. That's actually all you have to do. So we'll visit 0. Can 0 go to 0? Yep. 0 to 1?
7.
0 to 2? 0 to 3? -1. Or infinity. I'll put -1 for now. 0 to 4? Yep. 0 to 5?
1.
Okay. Which node do we visit next?
1.
5. Why is that?
It's the smallest.
It's the smallest that we haven't already visited, because 0 is the smallest, but we've already visited it. So we'll change this to a true. We're at 5. Where can we go? We can go to 3 and 4. So going to 3, 0, 1, 2, 3, what would be the cost to put here? 3, 0, 1, perfect. And the cost to go to 4 is
22.
plus 1, because we're at 1 right now. So 23. Because it took us 1 to get there. Notice we recorded how long it took, and then we're adding 22. All right, what's the next one we visit?
That would be visit 4, right?
4 is 23, which is greater than 7. We haven't visited node 1 yet.
Okay.
So we want to visit node 1.
Maybe it gets no on that.
It's okay.
I said 2 because the second line.
Oh, I see. So we're at 1. Where can we go from 1? Well, 2, it costs 250. And 250 plus 7, which is 257. Is that less than 450?
Yes.
Yeah, so we got 257. Where else can we go? We can go to 5.
290.
297. Is that less than 1? No.
You need.
No. So we leave that alone. And is that all we can do? All right.
Yes.
Now what's the next node we visit?
2. Wait, no. 2. Oh, no. 4? 23. So that's
23. So node 4.
4.
All right. So we'll turn this to a true.
You can only go back to
Where can we go from 4? Oh wait, we forgot to finish 1. I'm sorry. I lied. You can go from 1 to 4.
Oh, I didn't see that again.
Yeah, so that's 7 plus 125. Is that less than 23? No. Okay, so we don't need to do anything. Great. So now we go to node 4. All I can do is go to 0. So we're at 23 plus 17. Is that going to be less than 0? No. All right. What node do we visit next? 2. All right. 257. Where can we go from 2?
0.
We can go to 0. 350. Is 257 plus 350 going to be less than 0? Nope. How about 257? There, I cheated. 257. Right, so then what happens?
Wouldn't it be equal? So it'd be
261, which is lower than 301. So there we go. And then you visit the last one, but you'd never do anything with the last one because you already have the smallest.
How did we get 251 again?
61. Because it's 257, which is how long it takes to go from 0 to 1, or to 2, sorry. And then it costs 4 more to go from here to there. So we went from 0, 1, 2, 4.
Okay, got it.
That's how we got 261.
All right.
But notice we were just keeping track of what the minimum was so far. Okay. Everyone understand this algorithm?
Yeah.
Yeah, it's not, I mean, it's definitely more coding. You're going to have some loops. Got to get some,
It's going to be a hassle.
it's not, but it's not that complicated in my opinion. Okay, so Oh, that's beautiful. Okay. Let's get out of this. We're past lab time, but that's because we're not going to have class. All right. So there's 3 big ones left. You have depth first, breadth first, and Dijkstra shortest path. Which one would you like us to at least go through?
Shortest path. Did you say that was the most coded? Or
She did say that.
I would get you started on it, but I'm not going to do it. Actually, I take that back. I'm not going to do Dijkstra. You have to do that. I lied. I totally lied. Totally lied.
breadth first.
Breadth
Depth.
first.
I was thinking depth first.
Yeah, well, you said it's breath first.
Y'all chose breadth first.
The class has spoken. Perry has spoken.
Perry has spoken.
Show me what you got. Show me what you got.
Oh my goodness. Oh, I'm so sad. Why'd I load that up? Okay. Okay, I got rid of it. We'll just load up the browser in here. Maybe. All right. So I need to go. Was it C++Q? Maybe. All right. So we're doing a breadth first traversal. Okay. So we need to first come up with the Q. Here it is. Bum, 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 bum. All right, is it just, so we got push, pop, and front. Perfect. Okay, so std q of integers, and I'm going to call it to visit, and then I'm going to have std of vector of ints as visited. Okay, all right. So we're just going to start at the beginning. So for int I equals 0, I is less than m, num nodes, I plus plus. First we visit each node in order. So we have for int j equals 0, j is less than m num nodes, j plus plus. We're basically asking if m matrix sub I sub j is greater than 0 and visited dot, is it just contains? Oh. Should be like a find or insert or oh, it's a find. Okay, yeah, we're good. So j is not equal. I don't know why I called it vector. And is it called find? Let me see. C++ find algorithm. Load.
Page must get a lot of traffic or something.
They must. Oh my goodness. Oh, you just get an iterator to the beginning and and to the last? In beginning, last, and the value. Okay, cool. Dot begin, visited dot end, and j. If it doesn't equal visited dot end. So this is see if an edge exists and that node has not already been visited. If that's the case, then we go q dot push the node. Okay, great. While q dot empty, well, it's not empty. Let me make sure I got that function correct. It's empty. Yeah, it's a little weird. Yeah, So while it's not empty, And actually, we're going to visited. We forgot to add a visited up here. So, oops, visited dot push I. Actually, we also need to test to make sure it doesn't already exist. So if the element doesn't exist, if I is not already visited, let's go ahead and push it. We can go through all this, but it doesn't really matter. And then while the queue is not empty, we need to visit this.
I guess we need to rename all the places we say queue to visit, so that it does not complain when we try running it.
Whatever. Alright, in here. Oh, I did this the long, hard way. Sorry, guys. I am tired today. Whew. To visit for int j equals 0, j is less than nodes, j plus plus. Wow, I was tired. 4, boom, boom. We don't need this thing. Alright, so push the elements not already visited while the queue is not empty. For j is in there, and we're just push I. We need to pop it, so we need to go int v equals q dot front. Wow, I did it again. To visit dot front to visit dot pop. So we get the first element, and now we're going to go through all those elements, asking, hey, look, is there anything in here that hasn't already been visited? And if it is, go ahead and push it for each one. And then it just keeps looping like that. We do need to actually call visit on the node. And then we're done. Okay, let's first see if that's working. Actually, what do I call it? Just, okay. Now if I call it, alright, so now if we're down here and we actually typed all this correctly, which would be doubly impressive, breadth first traversal. Passing in print. Alright, let's see what errors we need to fix. That's what I thought. Oh, it's tmux, so I can't scroll.
What?
Yeah, you can't scroll because we're in tmux right now. Yeah, I agree. But I do already see a couple of errors that no one helped me with. Push back. Haha. Thanks, guys. Also, if we're in to visit, oh wait, to visit, and then we're going to visit it, then we actually need to go visited.push back on j as well. Alright, now let's see what happens. We're almost there. 983. J was not, oh, that's because we're visiting V. Push back. Visited.
We also need to change mnum to mnum nodes.
Alright, where's that guy? Mnum, there it is.
Yeah. Did we import algorithms?
No, we didn't. Does algorithm have an N in it? I keep forgetting. Whoa, it worked. It did something. Okay, so at least it called the function.
It's not visited, it's to visit. We don't want to mark them visited. Well, that's not good. All right, so you push it if it's actually in there, visited. If it's not, hold on. If we haven't visited it, you push it. While it's not empty, you call it. So I should do something.
Don't we want it to be equal to visited now?
Yes, that explains that. Now we're in a loop. Perfect.
Would that be the same thing with that last statement?
Well, hold on. Yeah. That'd be why. There we go. Perfect. Okay. Well, that was fun debugging. Let me go ahead and explain again. The outer for loop is to just enforce the fact that we need to visit every node just in case we forget one. When we're at a node, we see if we've already visited it. If not, we add it to the queue. Then we're going to have a queue that while it's not empty, we're going to keep visiting everything in the queue. So obviously when you have 0, it's just 0, and then the queue's empty, which is fine. You get that node, you pop it, you visit it, you push it to visited. Then you find all the nodes in that row that you can visit that you haven't already visited, add them to the queue, and then repeat with the queue again. You okay? Sounds great. All right, guys. Any other questions? Comments? Screams? All right, I'll go and try and commit this because this is not the actual repository, but that's okay. Well, I couldn't put my professor repository up here, otherwise you'll be able to edit it, right? Yeah.
That would be fun.
That would be fun. Well, for you, maybe. All right. Well, that's all for today. Again, no class Thursday. Yeah, you got about 20 minutes, but you have all this week to work on projects and homework. Is project 3 due tonight, or was it due yesterday?
I think it's due
It's due tonight. Okay, good. That's my thought. And then you can work on project 4. Excellent. Perfect. All right. Well, I will see y'all next week then. Have a good weekend.